All right, today we are diving into one of the most fundamental and maybe one of the most misunderstood components in all of electronics, the inductor. It's this unsung hero hiding inside basically everything, and by the end of this, you're going to understand exactly how it works.
So, to get us started, let me ask you a question. In the world of electronics, what component has inertia? What part is always resisting a change in motion, but not for a physical object, for electricity itself? Well, you guessed it, that's the inductor. And this is the perfect way to think about it. Seriously, picture a big, heavy, spinning flywheel. It's hard to get it moving, right? And once it's going, it is just as hard to stop. It just wants to keep doing what it's doing. An inductor does the exact same thing, but for the flow of electrical current. It hates sudden changes.
Okay, so let's get a little more formal and really define what this component with all this electrical inertia actually is.
At its heart, an inductor is almost laughably simple. It's usually just a coil of wire, maybe wrapped around some kind of core. But its behavior, that's where the magic is. Its entire job, its whole reason for being, is to push back against any attempt to change the current flowing through it. It just wants to keep things stable.
A great way to get a handle on the inductor is to compare it to its more famous cousin, the capacitor. See, a capacitor hates changes in voltage, and it stores its energy in an electric field. The inductor is its perfect counterpart. It hates changes in current, and it stores its energy in a magnetic field. They're like two sides of the same coin.
So how? How does a simple coil of wire pull this off? Well, the secret ingredient, the invisible force that makes this all happen, is magnetism. Let's dig into how this works.
This right here, Lenz's law, is the key to everything. It's a fundamental law of physics that basically says nature pushes back. Anytime you try to change a magnetic field, a voltage, or what we call an electromotive force, EMF, gets created that tries to stop you. This is the source of the inductor's inertia.
So here's how it all plays out, step by step. First, you've got a steady current flowing, which creates a nice, stable magnetic field around the coil. No drama, yet. But the second you try to change that current, the magnetic field has to either grow or shrink. And that change in the field, that's the trigger. It induces a new voltage in the coil, a back EMF, that pushes in the opposite direction of the change, trying to slow it down.
So if you remember one thing, let it be this. An inductor doesn't fight current itself, it fights the change in current. If you have a steady, direct current just cruising along, the inductor eventually just chills out and acts like a plain old wire. It's the starting, the stopping, the changing, that's what it resists.
All right, now that we've got the concept down, let's talk about how we actually measure this property. Let's put some numbers on it. This property of opposing current change has a name, inductance. We use the letter L to represent it, and we measure it in a unit called the Henry, named after the American scientist Joseph Henry. He was a brilliant guy who actually discovered this principle right around the same time as the legendary Michael Faraday.
Now, a whole Henry is actually a huge unit of inductance. In most of the circuits you'll actually see and work with, the values are way smaller, and that's why we almost always talk about inductance in terms of millihenries, microhenries, or even nanohenries.
Theory is great, but let's see what this looks like in a real circuit. What happens at that exact moment you flip a switch and send power to an inductor?
So, you close the switch, but the current doesn't just instantly slam to its maximum value. Nope. The inductor's back EMF fights it every step of the way, so the current has to wrap up slowly as that magnetic field builds. Once it hits a steady state, the inductor relaxes. But the real drama, the real action, happens when you open the switch. Now you're trying to make the current go from full blast to zero in an instant, and the inductor absolutely hates this.
Think about it. The inductor had all this energy stored up in its magnetic field, and by cutting off the current, you're forcing that field to collapse almost instantaneously. What is the consequence of such a violent change?
The inductor will do anything to keep that current flowing. And what it does is generate a massive voltage spike. The collapsing magnetic field induces a voltage that could be hundreds, even thousands of times higher than the original power source. This is exactly why you sometimes see a spark when you unplug an appliance that's running. That little spark, that's the inductor fighting back with everything it's got.
Now, this behavior might sound a little, destructive, but it's precisely this ability to store and release energy that makes inductors so incredibly useful. At the end of the day, that's what an inductor is. It's an energy storage device. Just like a capacitor stores energy in an electric field,
An inductor banks its energy away in its magnetic field. Every time current flows and builds that field, it's saving up energy. And when the current changes, it releases that energy right back into the circuit.
And here's the math that describes it. The energy it stores is based on its inductance, that's L, and the square of the current, I. This simple, elegant ability to store and release magnetic energy is the foundation for just countless technologies.
And this one property makes inductors total workhorses. In filters, their inertia is perfect for letting slow, steady DC current pass while blocking fast-changing AC noise. In your radio, they team up with capacitors to create a circuit that rings at a very specific frequency, letting you tune into your favorite station. They are absolutely essential in power supplies, using that flywheel effect to smooth out choppy electricity into a clean, stable output. They even act like little bodyguards, naturally slowing down that dangerous surge of current when you first power something on.
So, we've seen how a simple coil of wire can harness the invisible force of electromagnetism to act like a flywheel for electrons, resisting change, storing energy, and shaping the flow of electricity in so many ways. It really makes you wonder, doesn't it? If a simple coil can do all this, what other fundamental forces are quietly shaping the technology we rely on every single day?